Most major metropolitan areas are facing the growing problem of urban sprawl, loss of natural vegetation and open space. This has led to many environmental issues, health issues and increased traffic. These problems can be avoided with proper land and urban management, and from long time remote sensing using airborne satellites has been used for it. But these satellites are very expensive and difficult to operate. Moreover, the satellite images are particularly useful for detecting the major changes in urban land use. Additionally, the movement of people into urban areas has led to the problem of air pollution, and the conventional air monitoring systems are fixed and requires huge investment and maintenance. Apart from it, fixed station gives trends that are specific to that site and not represents the entire area. So here we propose a system which gives urban planners a clear statistical data about large areas of land, road mapping, land usage using autonomous quadcopter with onboard image processing techniques so that ground crews can save a lot of time by eliminating the labor intensive field work. Moreover, it informs us about the content of different gases in our atmosphere in different parts of our city so that quick action plans can be taken if air pollution levels near traffic intersections, busy roadways are exceeding the permissible level. Here is a comprehensive list of TI component used in our project. TIVA Launchpad, BeagleBone Black, Sensor Hub Booster Pack, INA 169, INA 122, PTS0808W, some voltage regulating ICs such as LM7805, LM7806 and LM1117. Our proposed design consists of various subsystems. Power to the quadcopter is given by two lithium-ion batteries of 11.1 volt 5000 mAh and 7.4 volt 2000 mAh batteries. The whole quadcopter nearly draws about 58 amperes of current, and these two batteries is capable of running this quadcopter for near about 30 to 35 minutes. The whole quadcopter weighs about 2370 grams. So we have used 4 BLDC motors, each of 1370 grams of thrust. These 4 BLDC motors are being run using electronic speed control, which gets the PWM signal from TIVA Launchpad. For balancing the quadcopter, we have used Sensor Hub Booster Pack, which runs the DCM algorithms on it after getting the sensor readings. This is current and voltage sensing circuit, which triggers a return to home command under critical voltage conditions. It also allows the copter firmware to compensate for the interference on compass due to ESCs and motors. This GSM module sends the atmospheric gas concentration, percentage vegetation, and tree count in a locality to the base station. Above GSM module, we have another TIVA launchpad which reads the analog data sent by the gas sensor module and send it serially to the BeagleBone Black. And at the top, we have the gas sensor module which measures carbon monoxide, carbon dioxide, ammonia, methane, ozone and the atmosphere. This XB is being used for wireless telemetry. This telemetry would be sending various parameters such as roll, pitch, yaw, the voltage and the current values for this quadcopter. The quadcopter navigation has become simpler and autonomous due to this onboard GPS. This is our OmniVision camera which is being connected via USB to this BeagleBone Black. These aerial images are being processed on this board. Now we will look the gas sensor modules in detail. Since large amount of current is drawn by these gas sensors, we can't continuously read them. Hence we have designed a relay-driven circuit for driving the gas sensors. MQ214, that is methane gas sensors, and MG811 carbon monoxide gas sensor require 6 volts of heating voltage, while other three sensors, hydrogen, ozone, and carbon monoxide gas sensor, requires 5 volt of heating voltage. These four sensors, MQ214, carbon monoxide, ozone, and hydrogen gas sensor load resistance are set such that the output voltage lies within the range of ADC of Stellaris, that is 0 to 3.3 volt, while the MG811 carbon monoxide gas sensor output voltage lies from 400 to 600 millivolts. So we have used an instrumentation amplifier INA 122 for amplifying this signal by the gain of 5.5, for which we have set the resistance value to 400 kilo ohms. Now I am sending the command read sensor to the GSM module. As soon as it receives the command, the relay circuitry turns on the gas sensor and it starts hitting the gas sensors for near about 60 seconds. And TIIC calculates the gas concentration in ppm, and the data is being sent to GSM module, and GSM module sends back the gas concentration to the mobile base station. Now you can see the gas concentration sent by GSM module is being received by mobile base station. We have used on-the-shelf software mission planner for our base station, which communicates with our quadcopter via Wavelength protocol. Now we will demonstrate that we can monitor the real-time voltage and current drawn by a quadcopter. So I am right now arming the quadcopter. Now the quadcopter has been armed. So you can observe that as I increasing the throttle, the current drawn by the quadcopter increases. You can feel the increase in the speed with the intensity of the sound, and correspondingly you can observe the increasing current in mission planner. And now I am reducing the throttle and the velocity decreases and current decreases down to 0. For power supply we have used PTH08080, which is highly integrated low cost switching regulator module, and it can deliver the current up to 2.25 amperes. The main advantage of using it in our project was its high efficiency, which is near about 95% greater than TO220 linear regulator IC. On the other side of this module we have INA 169, which monitors the current in the real time. This was our first flight without any sensors placed on the quadcopter, and we successfully flight this quadcopter till the height of around 30 to 40 meters. The final video demonstration consists of all onboard gas sensor and subsystems. Now I am sending the message read sensor to the quadcopter, and as soon as it receives the command, it will start hitting the gas sensor, and I have received the gas sensor data.
The quadcopter relays the sensor data and signals BeagleBone Black to capture image. We divided the system into two parts: plantation maintenance and plantation planning. For maintenance, we used predefined GPS coordinates and captured high-resolution images. Considering the fact that texture of plantation is crucial to state of vegetation, we segmented the background and image. The image thus obtained is converted from RGB to hue space intensity, and green pixels with value more than certain thresholds are removed in addition to red blue components of the pixels, giving us the infected side.
Multiple such quadcopters can move in coordination to analyze huge locality. Additionally, solar panels can be placed at the base station so that quadcopter can get automatically charged in critical voltage conditions. We are still working on this part of the project. In future, these copters can be used in accidental scenarios, forest fire conditions, emission control, and monitoring of critical areas as well as gas leak detection and localization.